Spectrophotometric Determination of Manganese in Steel, Lab Video Part 2. The unknowns and standard will be used to prepare standard addition samples for UV-vis spectroscopy analysis. First, 25 milliliters of unknown 1 will be pipetted into 5 separate beakers labeled A blank, A unknown, A standard 1, A standard 2, and A standard 3. Then 25 milliliters of unknown 2 will be pipetted into 5 separate beakers labeled B blank, B unknown, B standard 1, B standard 2, and B standard 3. Note, the experimenter accidentally changed the names of the unknowns midstream. Unknown is now unknown A, and unknown 2 is now unknown B. So just know that unknown 1 is synonymous with unknown A, and unknown 2 is synonymous with unknown B. So we're going to start by just rinsing out the pipette with unknown A. And now we can start filling the A beakers with 25 milliliters of unknown A. Let's speed this up a little bit for the next 4 additions. Now we're going to do unknown B, but we're going to rinse that pipette first with unknown B before we start. And we'll speed this up a little bit. Question 5. After pipetting unknown A into 5 A beakers, how important was it that the pipette was rinsed with unknown B before pipetting unknown B into the 5 B beakers? Explain. Now 5 milliliters of concentrated phosphoric acid will be added to all 10 beakers. First, we'll put about 50 milliliters of the concentrated phosphoric acid into a beaker. Be a little bit easier to pour into our 10 milliliter graduated cylinder. And let's speed this process up a little bit. Question 6. Why was it okay to use just a graduated cylinder to add the phosphoric acid to all of the samples, while a volumetric pipette was required for adding the unknowns? Now it's time to add our standard solution to the beakers labeled Standard 1, Standard 2, and Standard 3 for each set of beakers. This will be done with a buret. First, we're going to rinse out the buret with the standard. And then we'll put in just a little bit more and run some through the tip of the buret. Make sure there's no bubbles in the tip. Make sure we set the level of the buret where we want it. And then we'll fill the buret. We're going to fill it to the 10 milliliter mark. We're going to go a little bit above the 10 milliliter mark, and then we'll drain just enough out where we're at 10 milliliters. So now we're going to add 2.5 milliliters to beaker A, Standard 1. Now we're going to add 5 milliliters to beaker A, Standard 2. And then we'll add 7.5 milliliters to beaker A, Standard 3. And now we'll start with unknown B. We'll add 2.5 milliliters to beaker B, Standard 1. And now we'll add 5 milliliters to beaker B, Standard 2. And finally, we'll add 7.5 milliliters to beaker B, Standard 3. I would like to note here that this was assuming that the experimenter was able to zero in exactly on the values of 10, 12.5, 17.5, etc. If perchance you would have gone past those marks, you would have had to adjust accordingly for your next edition. Now 0.4 gram portions of potassium iodate needs to be weighed out, and the tare function on the balance will be used again for these weighings. We're just going to do one of them and assume the other 8 were done the same way. Oh, we need a little more. Good. Now the potassium iodate can be added to all of the beakers except the blank for each set. After this step, the beakers are ready to be heated. Question 7. Why wasn't potassium iodate added to the blanks? So here they're initially on the hot plates. They've begun to change color, being converted to the permanganate ion. And here we see that we've pretty much reached the completion of the reaction and the beakers are ready to take off heat. So the samples are now ready to be brought to 100 milliliters. First we're going to put the blank in there into volumetric flask BB. And we'll fill that to the mark. So now that we're on the unknown and the 3 standards, we're really going to want to make sure that we rinse that beaker out and get a quantitative transfer into the volumetric flask. Now we can bring that to volume with more deionized water. And finally, we'll invert that flask to make sure everything is properly mixed. We'll do the same procedure for our 3 standards. So there's our B set of standards, and so let's go through and do the A standards. So here are samples that are now ready for UV-Vis spectroscopy analysis. And you'll see that they're hopefully getting a little more concentrated as we go from unknown to standard 1, standard 2, and standard 3. Now we're going to go and use a Hewlett Packard UV-Vis spectrometer. This has a photodiode array detector that will be used to analyze the samples. So here's a real simple schematic. We have our light source over here. We have a tungsten lamp and a deuterium lamp for the visible spectrum and the ultraviolet spectrum. And it'll go through some filters and end up, this light will go through our sample. And then it'll come over here to a diffraction grating, and the spectrum will be spread out over this photodiode array detector that will take a snapshot of the whole spectrum almost instantaneously. So here's the actual instrument. You can see here that this is where the detector is at, that photodiode array detector. On this side we have our light source, and as we move around you can see there's an opening right here, and that's where the light will come out of the one side, and it will go through our sample, which will be placed right here, and the light will pass through to this side where it will be detected. So the way that we're going to put the cuvette in there is the cuvette has a frosted side and a clear side. We want to make sure the clear side is in the direction of the light path, and we're going to just put it in there and kind of lock it in there. Then when we're done, we're going to release that lock and take the cuvette back out. So now we can move on to setting up the instrument. The instrument is controlled with a PC, and so the first thing that we're going to want to do is just open up the program for the spectrometer. And you can see there's the lamps are down here. We can turn those on or off if we'd like to, but we're just going to leave those on for right now. So we're going to go up to the left part of the screen here, and we're going to choose fixed wavelengths because we want to look at two wavelengths in particular. So we're going to type in 525 for one wavelength and 900 for the second wavelength. And then since it is a photodiode array detector, it will display the whole spectrum. So we're going to type in 400 to 950 nanometers for the spectrum that it's going to show us. And so now we're ready to start analyzing our samples. Now we can start analyzing unknown A. We're going to start by scanning a blank. The purpose of the blank is to let the detector take a snapshot of what 100% transmission looks like. By doing this, the instrument knows what it should subtract out of the spectrum for the light that is being absorbed from the samples. Since all of our samples are aqueous solutions, it makes sense that water would be used for the blank. So we don't need to pay a whole lot of attention as to what this means, only that there's a nice open window for the range of absorbance that we want to look at. So let's start scanning our samples. The first thing we're going to do is scan the solution blank. And so we'll fill up the cuvette once, and then we'll fill it up again with the blank. And we'll wipe off any liquid that might be on the outside of the cuvette using a lint-free cloth. Insert it into the instrument, and now we're going to start hitting the sample button. So here's a spectrum of our blank, and initially it looks pretty ugly, but we need to remember that the numbers on the y-axis here are extremely small. So now we can do our first sample, colored sample. This is the unknown with no standard addition added. So now we're going to fill up that cuvette twice and dump it out each time, and then fill it up a third time, and we'll scan that. Again, we're going to wipe off the cuvette, make sure we don't get any liquid into the instrument. And we'll go ahead and scan this one. And the nice thing about this instrument is that it overlays our sample. And now you can see that the blank is way down here, and you can see that there's no significant absorbance from the blank, and that at 525 nanometers, the permanganate ion is absorbing at its lambda max, and that there should be no absorbance over here at 900. So now we can move on to our unknown with standard addition 1. Make sure it's mixed up. And we'll follow the same procedure. We'll fill the cuvette up twice and dump that out to make sure that we have the right concentration in the cuvette. Always want to make sure we dry off that cuvette. And we'll scan this one and see what we get. And there we go. And this is a really good sign. We can see that our sample with the first standard addition has more absorbance than just our unknown without that standard addition. And we can see down here that all of our numbers are being recorded, so we can record all of our absorbance values when we get done scanning all of the samples. So we're not going to show the cuvette being filled anymore, and we're just going to move on right to our unknown with standard 2. Here you can see we have added absorbance again, which is a good sign. And all of our numbers are accumulating down here for our absorbances. And let's move on to our last sample, which is the unknown with standard addition 3. So these absorbances look really good. And down here, we're going to write down all of these numbers. Here are absorbances at 525 nanometers, and here they are at 900. And let's type these in here just where we know, or we can remember what absorbances correspond to what samples. Okay, so make sure to record these absorbance values for unknown A. Question 8. Why is a cuvette with deionized water used for a blank for this experiment? Now we can move on and analyze samples for unknown B. So here's our blank. Like I said, it looks really ugly, but we have to keep in mind that these numbers on the y-axis are extremely small. Let's move on to our unknown with no standard addition added. Now it looks good, and you can see that this solution blank is insignificant compared to the absorbance of our actual unknown. Let's move on to our unknown with standard addition 1. That looks good. So let's move on to our unknown with standard addition 2. And now finally, let's do our last sample, and that's our unknown with standard addition 3. And there we have it. So here we have our absorbances at 525 nanometers, and here we have them at 900. So make sure to record these absorbance values for unknown B. Remember that absorbance at 525 nanometers is at the lambda max of our permanganate ion, and this absorbance out at 900 nanometers is where that ion should not be absorbing light at all. So this number is really just accounting for the drift in the baseline of the instrument. So for all of your values for both unknown A and unknown B, make sure you take this first value and subtract out the second value for your corrected absorbance. And this concludes lab video number 2.